Well, here we go. A new Lewis-Dot structure with a couple of little twists in it that we'll have to deal with. So this is worth going over. The substance we've got is officially called methanoic acid. Meth means one carbon, typically in organic chemistry, and this is an organic compound, so we've got one carbon, and the acid is the OOH. It has an older name, formic acid, and very often you'll see how that shows up. In fact, many acid products with an FOR in it, with this basic, this COO, HCOO, deals with formic stuff, things like formic, formate, and so forth. So poor organic chemistry students have got to live with two naming systems. Okay, we've got methanoic acid. We've got to do a Lewis-Dot structure for it, and this is going to be messy because you say, how am I going to arrange these things? But you needn't worry about that because in AP Chem, they will set them up for you. They know that there's too many possibilities, so they'll say, this is what the molecule's arrangement is. They'll put the carbon here and say, okay, you take it from here. So, like I say, don't worry about that. They've always given structures for organic compounds and had students fill them in. So, naturally, our next step is what we do with all Lewis-Dot structures is we start counting. We count valence electrons, 18 of them. And always double check, because if you get this part right, you're going to have to go all the way back to the beginning, and you're not going to have time. 2 hydrogens, that's 2 electrons. A carbon is 4, so we got 6. And then we've got 2 6s, which is 12 plus 6, 18 valence electrons. It's an even number. That's pretty much what you expect. I would double check again. It's worth a few extra seconds now because it'll create a lot of pain later on. Take it from me. I've gone through the pain. Okay, now, next step is drawing the bonds between these things, just as we always did. And we put a single line between each one of these things that represents 2 electrons. So that's going to simplify things for us because we have 2, 4, 6, 8. We've got a total of 8 electrons already taken care of, and those 8 electrons are in our bonds, 2, 4, 6, 8, yep. So we have 10 remaining electrons to distribute. And this is not too bad. We put them on the surrounding atoms. The carbon pretty much looks like our central atom, and usually we save the carbons for last anyway. So let's put those 8 electrons out there, and let's see, 10 electrons, pardon me, 2, 4, 6, 8, 10. Okay, that leaves 0 electrons left behind, and we're in pretty good shape right now. We've got what looks like to be a pretty decent Lewis structure that we can handle. And we start looking for things. We say, okay, hydrogens, don't worry about a bond and they're gone. This oxygen has 2, 4, 6, 8. It has its low potential energy octet. And this oxygen does too, but our carbon's missing something. 2, 4, 6, it doesn't have the octet, but that's easy enough to take care of. However, you might say, well, I know that I'm supposed to take a pair of electrons and slide them over to make a pi bond, a second set of shared electrons. But which oxygen do I take them from? There's some rules that'll help you later on. But right now I look and say, hey, oxygen normally ends up having 2 single electrons. It usually makes 2 bonds if it can, and the oxygen here has 2 bonds already. So I would favor taking a pair of electrons from here. Let me take this spot. Let's take this one and move them over. There we go. Now let me slide it over just a touch. Come on. Yeah, that looks better. Our carbon has 2, 4, 6, 8. It's got a pi bond, a double bond. Our oxygen has 8. And again, our oxygen has 2 bonds, and that's usually what you'd like to have it in its arrangement. Because remember, oxygen has those 2 unpaired electrons, this original arrangement. There'll be more about that in formal charges. So this looks pretty good. It looks like we've got a Lewis-Dot structure for this organic compound. Yeah, you're an organic chemistry student. Voila! Now, whoops, no, forget that. Now let's go to here. This is the diagram I wanted. Okay. Here we go. Everything's in place. Now we need some descriptions. This double bond, you'd say, well, I could have made the double bond here, but that really changes things because this has got a hydrogen and this doesn't have a hydrogen. So there's no real ability to make an equivalence. So this double bond stuck in this location. There is no resonance here because the two possible locations for the double bond, even though one here is preferential, they're different. So this double bond is pretty much stuck in this place. By the way, this is a common structure for all organic acids. It's worth remembering CO or HU. CHU is our acid, COOH. And one of the oxygens is double bonded and the other one is an OH. It'll save you time. Theoretically, you don't have to know organic chemistry for AP, but it sure can save you a lot of time on FRQs. With no resonance, we know we've got a double bond here, and double bonds are stronger, and they'll pull atoms in closer than single bonds. So if you're asked for bond lengths, relative bond lengths, you would expect that this oxygen to be closer to the carbon. We'd have a smaller equilibrium bond length, about 123 nanometers, and here we've got 136. I'll bring this up later when we do our next substance. Now, let's go to our steric numbers. We've got basically two things we can worry about in terms of steric numbers. We've got this oxygen, which has two bonds, and it has 1, 2, 3, 4 pairs of electrons on it. So it's going to have a steric number of 4, and we'll get to that shape and the angles involved because of that. This carbon has, or right here, this is our other central atom, has 1, 2, 3 bonds, and we don't count a pi bond. So this carbon has a steric number of 3. It's going to be an sp2 hybrid. And this shape is going to be quite different than this shape. So there's the Lewis dot. There are some new things in here, and you might want to review doing this because this is a common type of AP question where they'll give you a structure and have you fill it in. So, okay, you've just done your organic chemistry of methanoic, or if you really like to use archaic, which I sort of like. I like formic acid, sounds a lot nicer to me than methanoic acid. Okay, I'm closing down.